So fluid conservation of momentum is obviously very important. It's basically the only reason that this spacecraft is able to fly. So the fluid momentum is conserved, so the fluid has a certain velocity that's going downwards. Um, and since momentum is conserved, that pushes the spacecraft upwards. So key points from last lecture, which was on conservation of mass. We talked about control volumes. We talked about the integral form of conservation of mass. So an important thing about the control volume is that it has this unit normal vector that's always pointing outwards from the control volume surface. And we have an integral formula of conservation of mass. So on the left-hand side is accumulation, which is the time rate of change of mass in our control volume. That's a volume integral of the density. So accumulation is equal to the net flux into our control volume. So the net flux in is an area integral around the entire area of the control surfaces of this quantity rho v dot n dA. So that v dot n, something we're going to see a lot. So it's a vector dot product, which produces a scalar. And the direction of that, I've snipped kind of an important part of last lecture where we talked about the different um, directions. So when v dot n is less than 0, that means we're going in because the vectors are in the opposite direction. That's kind of the tricky thing. So that's the reason that we have the negative sign there. So that automatically makes this net flux in. So that will be positive when v dot n is less than 0, because that will be less than 0 and then you have a negative sign. So that's positive inwards, which matches what we expect for our accumulation. So our accumulation should be going up when there's a net flux in. And at steady state, we have accumulation equals 0, which means all the different fluxes in and out of our control volume are balanced. Today, I'm going to do a conservation of mass example and move on to conservation of momentum. That's what we'll also cover in our second lecture. So it's going to be hopefully an examples heavy day, because this part of the course is all about examples. You'll get a feel for the problem types, and they all start to look the same after a while. So once they start to look the same, that's how you know you're well practiced. So we're going to analyze mass conservation for a simple control volume in the first example. Then I'm going to give you the integral form of conservation of momentum. We won't derive this until the next part of this module where we talk about Reynolds transport theorem, but I'll give it to you today, and then we're going to do some examples of momentum conservation for simple control volumes. You might be happy to know that we don't always have to use that horrible looking integral form of this equation. So I'll give you basically a simpler form of the equation that you'll use for, let's say, 90% of the problems in this class. Sometimes we have to do an integration, but it's almost never going, it's never going to be an area integral or a volume integral or anything like that. You'll see what I mean by that. Okay, so as I said, we're going to do conservation of mass to start. I'm just going to review the equation we have for conservation of mass. D by dt, this volume integral, is equal to this area integral into area integral here. Okay. So is conservation of mass, maybe someone can tell me, is conservation of mass a scalar or a vector equation? Scalar, right. So mass is a scalar, so we expect conservation of mass to be a scalar. We're going to see later on when we do conservation of momentum, momentum is a vector. So that area integral is going to produce a vector. So we're going to do an example here of conservation of mass. So this example is going to be about a stream tube around a wind turbine. So let's draw a picture here. Okay, so let's say we know the location of a stream tube around this wind turbine. Say it does something like that. So assume we know the red line part is a stream tube. That's the first thing we're going to say we know. The second thing is say this, by the way, this is the sort of thing that will be given in a problem. It's not an assumption you have to write down. We're going to say uniform inflow and outflow. Uniform meaning the velocity at the start of this stream tube is all the same across the entire area. Same thing at the outflow. So we have the same velocity here. We don't have some sort of velocity profile. It's just all the same across that entire area. And we're also going to give the area of the inlet to our control volume. So that'll be 2,300 square meters. The area of the outflow is 6,000 square meters. Say we measure the wind speed in front of this wind turbine and it's 5 meters per second. We also know this is a steady state flow. So these are all the things. This is the problem setup. I'll show you what this stream tube looks like in a second. But so this is our problem setup. And the question is that we're trying to solve is what is V out? So we know V in. We want to say get the velocity, the uniform velocity at the end of this stream tube. So we're going to basically define a control volume around this object. The front of the control volume will be the front of this stream tube, and the back will be the back of the stream tube. Since we know the location of this stream tube, it's a very convenient choice for a control volume. That's stream tube is convenient because we don't have to account for inflow or outflow through the stream tube, because we know a stream tube is a set of streamlines, so flow can only be tangential to that stream tube. So there's no mass flow. For example, there's no mass flow that goes this direction. We know that all of our mass flow is going to basically enter this control volume at the front here and leave at the back. This isn't something you can assume for every problem, but this is our first example, so we're going easy basically. So just to make this drawing clear as to what I'm trying to draw here, this is a 3D image of what this looks like. So this is kind of some wind turbine analysis works like this, where you assume a stream tube. So it's a 3D. So we kind of have a circular area, and then the stream tube goes around this wind turbine, and the outlet area is a little bit bigger. So this is kind of, I'm drawing like a cross section of this. Okay. So our conservation of mass says that d by dt, this volume integral, it's the negative area integral rho v dot n hat dA. So since it's steady state, we can get rid of this volume integral. So that's 0 equals the negative area integral on the right-hand side. Remember, this area integral is over the entire control volume surface. So the entire green kind of green dashed control volume there. So since we have, we can break up an area integral over something like this into a set of different area integrals. So um, it's going to be a sum of something like this. So say we can do the area integral over the inlet. I'm just going to break this up so it's clear what I'm doing with the negative signs. So this area integral, since we have a couple of kind of discrete areas, we can just break that up as a summation of our different area integrals. And also we know that we have constant, so we're going to assume that we have constant density, velocity, and constant unit normal vector along the inlet and outlet. So maybe the constant velocity was given in the problem. The constant density is something we can assume. One sec. The constant unit normal vector is that we have kind of a planar surface. So the unit normal vector along this entire surface is going to be constant. So for example, on the top of this, the unit normal vector is changing. So you would have to sort of know how that changes in order to do that area integral. Lucky for us, that's a streamline. So we don't have, so basically v dot n is always 0 there by definition of a streamline. Yep. Yep. So the second term is at out. So yeah, I'm just breaking this up into an addition of the area integral here plus the area integral here. We could, in some problems you'll see, we'll break this into a summation over the entire. So we'll do one integral there, one integral here, one integral here, one integral here. But for this problem, because of this very convenient stream tube, we only need to do the inlet and outlet. Any other questions so far? Okay, so our area integrals are going to become much simpler now. We have 0 is negative rho v dot n hat inlet minus so we've basically pulled everything that's going to be constant out of the integral. So the area integral of the area is just the area. So we don't actually have to evaluate the area integral since we know this area. So that's not a problem. For example, this is just going to be the area of the inlet, area of the outlet. But let's talk about this dot product now and what this evaluates to. So remember, this is a vector, the velocity vector. The velocity vector at the inlet is vn 0. Did I do x and y? Okay, I'll define our coordinate system just. So our inlet velocity vector is just some vn in the x, and there's no y component of that. What about our normal vector at the inlet? What would that look like? So remember the normal vector points outward. So it's like this. So what will that look? Yep. Negative 1 and 0. Yeah, exactly. And remember, that's constant along that entire inlet face, which is why we could pull that out of our integral. V out is in a similar manner. And n hat out is going to be 1 and 0. So n hat out is 1 and 0 because our normal vector points outward always. So that's pointing in our positive x direction, right? So positive x is to the right. So all of our velocities are to the right. and our normal vector will change depending on whether we're in the inlet or the outlet. I'm normally not going to go into that level of detail about these vectors, but if you have questions on where certain negatives come from, that's I would say the main source of error that's going to be in this part of the course is wrapping your head around the negatives and the dot products. So yeah, if you ever have questions about that, let me know. But so we're going to get 0 is negative rho. So that dot product will be negative Vn because V dot n here is just negative Vn. An minus rho V out, A out. So I'm just gone from this line, evaluated these area integrals as just like A out and A in, and then this dot product I showed you exactly what those vectors are here. So the dot product of this dotted with this just produces negative Vn. Again, negative Vn is just a scalar. So the dot product takes two vectors and returns a scalar. So that's why we get a scalar. Same thing with V out. So we're going to get V out is Vn An over A out. Which is 1.92 meters per second. So I gave the areas of these sort of boundaries of our stream tubes. So if we know the velocity at 1, we know that mass is conserved throughout the stream tube. So we can basically determine the speed at which the mass is leaving. Yep.
With the double integral area, it just doesn't make sense in my head, right? A squared over 2.
Because it's an area integral. So it's like a dA is maybe in Cartesian, that would be like dx dy. So you do the first integral of, say, dx, which is x, and then the second integral of dy, which is y, so xy, which is area. So it's not like you're integrating the area twice. Um, say you have a box and you're doing an area integral of dx dy. So you do the first integral, x would be, say, you integrate over x, and then you integrate over y, right? So this is like integrating the area integral over dA. So that would just say be xy, which is a, and then this one is just a. So delete that. Yeah, no problem. Any other questions about this example? Okay. So I'll give you the nicer formula now. So normally you don't have to go into that level of detail with the integration. That's because there's some important assumptions that allow us to skip having to write down these integrals. So those assumptions are, so make sure you check these assumptions before you use these formulas because they won't hold in all problems. So for steady state flow with constant velocity or average velocity. So we're going to do some pipe flows, you'll see. Okay, so for steady state flow with constant or average velocity, inlets, outlets, maybe I'll say planar inlets and outlets. Planar is important because that normal vector will be constant along an entire inlet outlet. You can just jump straight to this equation. So you have to sum over the outlets, m dot, minus summation over the inlets. I'll just say n. Equals 0. So this is just basically the flux. The accumulation is 0 since it's steady state. And this is the net flux. So if you see in the problem setup, like we have for this problem, that we have constant velocity inlets and outlets with constant, that are planar. It's a steady state problem. You can just go right here to this m dot. Yeah. I wouldn't say that we have more volume. I should say we have more area. So this is an incompressible flow, so it has constant density for sure. The I wouldn't say the volume expands like this. So yeah, I wouldn't say that the volume expands. I think the density is for sure constant. Um, so I wouldn't think about this as the flow sort of expanding to fill a bigger void in space. I would think of this as sort of, since the density is constant, that when that area starts expanding, the flow has to slow down because it has to fill, like with the same density, it has to fill a bigger area in space. Does that make sense? Um, this isn't accumulating. It has to sort of slow down because the area is getting bigger. So since our density is constant, if you have to fill a bigger area as you're moving, you have to slow down or else your density will decrease, right? Sorry, I don't know if I explained that well. Any other questions about this problem? Okay. Mass conservation is definitely the simpler part of this chapter, especially once we start applying this outlet. I'm also just going to remind you of what m dot is. So m dot is rho v dot, which is rho v a. Okay. And also the nice thing about this is we just need the mass fluxes here. So there's no vector dot products, no signs to worry about. So that's just straight up scalar. So what's the mass flux into our CV and what's the mass flux out of our CV? Yep. Uh, this applies to flows that aren't just in the stream tube. So if there was flow outside of the stream tube boundaries, we would just account for that as an additional outlet in our summation there. But we would have to assume like constant velocity and constant n hat along that, which wouldn't be. So if we had flow for this, it wouldn't. You couldn't use that equation. Yep.
How would you approximate the nodal vector at like the edge at the corner of a square? Like let's say you had flow coming out, how would you approximate
At the corner of a square here, like so, if you had say flow coming through a square like this, well, so that corner is a point. So you can't really have a flux through a point. You need a flux through an area. So you would do, I wouldn't worry about that. You could just do like an integration along this face and then add it to the integration along this face.
So we just ignore that small point there where it comes to boundary.
Yeah, so I guess if you zoom in like all the way on the corner, you're saying like there might be like flux through there. This this is like in the limit, this is a single point, right? So you can't have a mass flow rate because the area will go to zero because it's a point, right? So you can't really have a mass flow through a point. So any other questions? No worries. Any other questions? Okay, so let's do conservation of momentum. So I said last lecture, in a conservation law, we really only have two physical processes, right? What are the two physical processes? Yeah. Accumulation and flow, right? Yeah, thank you. So yeah, accumulation and flow or flux. So we have accumulation and flux. So we can't create or destroy in a conservation law. So we have no source or sink term. So for conservation of mass, which is what we just did, we can't change the total mass of our system. So in this case, the accumulation is equal to the net flux. That's what the equation tells us. So in other words, accumulation minus net flux 0. Again, I'm saying net flux in, but I don't want to write that every time. So accumulation minus net flux equals 0. Basically, the accumulation minus the net flux tells us the total mass of our system, and we know that that can't change, so that always has to be 0. So this is not the case for momentum. So how can we change the momentum of our system? Say we have a control volume. How do we change the momentum of the control volume? It's just Newton's second law, right? Yep. Apply a force, right? So you can change the momentum of something if you apply the force, if you apply a force to it. There's no way to apply a mass to something to change mass without affecting mass conservation. But for momentum, we can change the system's momentum applying force. So Newton's second law is really about momentum. And this is a vector equation. So we have vectors on both sides of the equation, which is expected. So we have mv, that's a vector, and we have the forces here. So in Cartesian coordinates, we have x, y, and z components. So this is actually really 3 equations in our Cartesian frame of reference. So we should get basically for momentum, we get accumulation minus net flux is equal to the summation of forces. Maybe I'll put a vector there because this is a vectored equation. So our accumulation now should be a vector and our net flux of momentum should be a vector. So what this looks like, and I'm not going to derive this right now, so I'm going to wait until we do Reynolds transport theorem to basically derive this. So this is partial by partial t. Of rho v dv. Okay, so pay attention to my v's. So the v with the ticks on the end. This v, that's volume. So we're basically doing the volume, the time rate of change, partial by partial t, the time rate of change of rho v, vector v. So that's kind of the time rate of change of momentum, which is our accumulation, plus this area integral. That same thing, times v dot n hat dA. is the summation of forces on our CV. So this is considered the integral form of conservation of momentum. I'm not sure if we'll have time for it in this course. Plus, I know you guys might not care that much, but you can actually derive Navier-Stokes from this integral form of conservation of momentum. So we built it up from a differential control volume. Sorry, not a control. We built it up from looking at a fluid parcel, analyzing like the forces and shears and stuff like that on it. You can also derive it from this equation going downwards. Yep. So we have a vector, right? So this produces a scalar. V dot n is a scalar. So this is a vector. So what this is it's the net flux of momentum. So we'll see in Reynolds transport theorem how we get kind of net flux of something in general. But you can know that we're sort of convecting momentum through a surface with some sort of velocity. So this is the velocity that we're convecting it through a surface by, v dot n, because it's the normal component. And the thing we're convecting is rho v itself. So this might become a little bit more clear in Reynolds transport theorem. But yeah, we get velocity itself. So this is very confusing, I know, because you're not used to seeing like vectors times vectors and dot products. So the thing in the brackets produces a scalar. And that scalar is just the normal component of the velocity vector. And rho v is a vector. So we get scalar times a vector times a scalar. So that's just a vector again. Any other questions? Good. So let's talk about the terms in this equation. So our control volume itself has a certain mass and a certain velocity. So our control volume can be moving. So our control volume has its own changing momentum. So you'll notice that's a time derivative, so that will be 0 for steady state flow. But in general, you can actually, the control volume is something that takes up space, so it has a certain momentum itself that we have to integrate to find that. And so we can change the control volume's momentum by flowing things in or out of it, and applying forces to it. So if the momentum of our control volume isn't changing, for example, if it's steady state, that means that the forces that we're applying to our control volume are equal to the momentum change created by flowing things in and out of our control volume. And again, this is a vector equation. So in a vector equation, we should expect each of these terms to be a vector. So this is the volume integral of rho v, which is a vector. And I explained here why that produces a vector, and obviously summation of forces is a vector. Before I do examples, I will give you the sort of easy version of this equation, like I did with the mass conservation after. So it's the exact same assumptions. So steady state flow with constant velocity. I'm saying constant or average velocity because we're going to use this for a lot of pipe flow problems. And as we know, a pipe doesn't have a constant velocity across the cross section, but we usually just use the average velocity. Constant or average velocity. Planar inlets / outlets What else? Okay, that was it. So we can use the following equation. So we sum over our outlets, m dot v minus the summation over our inlets, m dot v. So again, this is a vector equation. So we need all those assumptions in order to pull things like the mass flux out of the. For example, if you do constant, if everything is basically constant in here, the integral of rho v dot n dA, that gives us m dot. So that's where that m dot comes from. And then this v comes from the remaining v. So I would say the rest of today is going to be examples of using this. There's a lot of different types of problems you can see, but they're all going to start to look the same. The setup for most of them is you apply both conservation of mass, conservation of momentum to them. Usually conservation of mass allows you to determine kind of a missing velocity that you need to solve the problem. Once we know all of our velocities, we can determine a force. There is a certain type of problem that I'll show you an example of where we can't assume this constant velocity. Usually that's only across, say, an outlet or something like that. So we have to integrate along an outlet, some sort of function. So let's do an example. We're going to take the same wind turbine stream tube example. And the example is calculate the force on the wind turbine from before. In order to calculate this force, we actually need the density now. So we didn't need density when we did conservation of mass, because the density will cancel usually. So we'll take rho equals 1. So a reminder of what we had. Something like this. And our CV was like this. So our CV is a region of fluid. And the momentum change of our fluid will apply a force to this wind turbine. It's, okay, so let's see. I'm going to write down just the velocities we used. 5 meters per second, 2,300 meters squared. We determined from conservation of mass that this is 1.92 meters per second, and that has area of 6,000 meters squared. So for conservation of momentum, pressure also applies a force to our CV. So we're going to say this is P atmospheric. Let's see. Gee, let's hold off on doing the. I'll keep that in there. Okay, we'll do P atmospheric. Okay, so I'm going to use the equation I gave above. So summation of the momentum coming out of our CV minus the summation of the momentum coming into our CV is equal to the sum of forces. Since we have the same, this might be a little bit confusing. So we're not going to have a net pressure force on our control volume here. You might think, okay, if the pressure across this entire face is P atmosphere, the pressure across this face is also P atmosphere, this one has a larger area. so it would apply a net force. But the pressure is also P atmospheric along here. So you can think that the pressure would apply a force like, it would apply, say, a force like this, which would cancel the leftover parts of this force. Same thing on the bottom. So I'm not going to include pressure in our force balance for this problem. For pipe flows, that's where pressure starts to come into effect. So the first thing we do is draw a free body diagram of our control volume. So there's some force X being applied. Okay, so the mass flow rate in is going to be the mass flow rate out is rho V out A out. So remember, m dot is just rho V A. We're going to look at the x direction here because that's the x force that we want to calculate, the force on this wind turbine. We don't have any inlets or outlets in our CV in the y direction, so we're not going to create any net force in the y direction, right? So if you looked at the y direction, you would get this is 0, this is 0, so therefore the forces have to be balanced in the y direction. So that is m dot. V is in the x direction is V out minus rho V in A in V in. Okay, so we get the x force being applied to this control volume is 35.4 kilonewtons. So wind turbines are pretty big, so they experience very high forces, basically. Yeah, so okay, any questions about this example? We have m dots. This basically just boils down to m dot, calculating that, and calculating V out here. So yeah, sorry, I know I asked for questions, but give me 1 second. The thing you have to watch out for the signs is in this vector, because this is a vector component, right? So if one of these V outs was in an opposite direction, we might have a negative there. Okay, so any questions? I guess I'll, yep. Just Ben? Yeah. Where is that force? That's a good question. Yeah, I would say, I don't know if you can exactly pinpoint where that force is being applied. That's just the force on this object in general, like the force on our kind of CV. It's a region in space. So the net force is, yeah, I would say that's just being applied there. The exact location of the force is something you have to determine like with further analysis, because you have to like integrate the pressure on, say, this wind turbine or something. Yep. Total. Yeah, just based on the momentum change of the fluid, we know that there's a net force somewhere in this control volume. Yep. It's on the air. Yeah, it's equal and opposite, right? So uh, let me think. Yeah, maybe this FX should be the other way. So the force that the wind turbine applies on the fluid CV is to the left, I guess, right? Because you expect the wind turbine to blow. Yeah, good point. Okay, let's redo that. So Fx should be negative here. Okay, so let me explain. So we expect the wind turbine, obviously a wind turbine should feel force kind of in that direction. But since the force is equal and opposite, the force that the wind turbine applies on the fluid is actually in this direction. So this will be negative Fx. So that Fx is the force that the wind turbine applies on the fluid, which is in the negative direction. But we'll just take, say, the magnitude of this, or the force that the fluid applies on the wind turbine is opposite to this. So yeah, if I was to draw Fx in the opposite direction, it'd be a propeller or some sort of propulsion device. So that's not what wind turbines do. They wouldn't be really useful if they just fed the wind up. We want the wind to turn them.